Today, I'm honored to have the privilege to introduce our guest speaker, Mr. Aditya Viswanathan. Mr. Aditya Viswanathan started his career as a biomedical engineer in SRM Hospital, Katangalattu. He played a key role in radiology department, cardio intensive care unit, and cardio OT. Later, he moved to Germany for doing his master degree in medical system engineering at Otfon Eureka University, located at Magdeburg. Our speaker academic activities are evaluation of CT detector design, constructor detector design in GN4, stimulated X-ray interaction using Monte Carlo stimulation. His research activities are imaging phantom using Siemens Artis Zigo CM system, track displacement using Meophase tracking system for the development of 2D to 3D registration method. On behalf of Savita Engineering College, I welcome you everyone for this webinar, Medical Image Processing Using Python. Now, I hand over the section to our speaker, Mr. Aditya Vishwanathan.
Thank you, Mr. Madanlal, for that introduction. And I would like to start by thanking Dr. Murthy, Head of Departments of Medical Electronics, and also Biomedical Engineering and Savita Engineering College for giving me this opportunity to share my experience and knowledge in the field of medical imaging and biomedical engineering in general. And I'd also like to welcome all the participants, and we will start with the presentation now. So this presentation in general will not only focus on image processing using Python, but also various other applications of medical imaging and various other tools which are used for medical imaging. So we will go in a gradual manner and then lead finally to image processing using Python. And so for every single field of study you choose, there is always a reason why you choose it. So it is always important to decide why you choose medical electronics or biomedical engineering. And there will be multiple reasons for you to choose it. So depends on your interest, right? So medical electronics basically deals with development of hardware and hardware such as circuitries, sensors, and your ADCs, any hardware which is basically used to acquire signals and use these biomedical signals in order to create more applications is what medical electronics is all about. So if you had interest in this area, then medical electronics will be a very good option. And once you have created all the electronics and circuits for acquiring signal, then the acquired signal could be analyzed using signal processing techniques, and also these signals could be used to create end applications. So this is one important field in biomedical engineering. And there is also rehabilitation engineering, which uses this created medical electronics, and not necessarily medical electronics, it's also about biomechanics, where you can use various mechanical structures, create various mechanical structures based on the patient's need, and then use these structures to create assistive devices. So for example, there is a video on YouTube by Dr. Hugh, Hugh Herr, and he talks in TED Talk about how he became an amputee. He lost his leg, and how he used medical engineering or biomechanics in order to make his own robotic leg. So rehabilitation engineering is also another field, and medical imaging is where my interest comes. So how do you visualize structures inside your body without opening the body? So that is basically the mystery which is solved using medical imaging techniques, where there are various medical imaging techniques such as diagnostics. And in diagnostic medical imaging itself, there are 3 to 4 or even 5 different modalities of imaging techniques. And also in therapeutic, where we use indirectly image our object and also do therapy at the same time. So medical imaging is what I will be concentrating on today. And there are many more fields in biomedical engineering and medical electronics application based. And the next one is also medical application development. So everything is not about hardware. So developing hardware is of course important, but developing software is equally important as developing hardware. And software doesn't only mean applications in terms of just algorithms, but also it deals with UI and GUI, UI user interface and other tools which are useful in order to have a good utilization of your hardware. And this medical software is actually in a very good rise because of all the availability of new hardwares and computation power these days. And also the next area of interest would be surgical equipments and assistive devices. So surgical equipments start from your basic scalpels to all the way up to any kind of implants. So if your interest is in material science and mechanics, then surgical equipments will be of a really interesting area. And these surgical equipments and assistive devices, they are basically used to change or transform the lives or improve the lives of patients in healthcare. So these are just some areas in biomedical engineering that uses medical electronics and other technologies. So it is always important to find your area of interest, and the reason you chose biomedical engineering or medical electronics will of course fall into some of these category, if not maybe something else that I did not mention. So I personally started my journey into biomedical engineering because I saw a video on Discovery Channel long ago. And this video, scientists were basically trying to create a human, or not exactly a human, but a robot, which had all the functioning capabilities of a human, except a real human organ. So they created an artificial heart, which was a pump, and the artificial pancreas, artificial liver, using sensors, using electronics, using mechanics, fluid simulation or fluid dynamics. So it was basically the application of science and engineering in the field of medicine. So this interest, you would have had some kind of interest, or you will have some interest to pursue or to motivate you to choose certain studies. So once you have this interest, then you, in your undergraduate studies, you find your motivation as to, okay, now I have this interest, now how do I proceed? So once you have this interest, then in your undergraduate studies, you basically have an overview about all these different areas. So you study a little bit about medical electronics, you study about signal processing, you study about sensors, you study about various other sub subfield in the area of biomedical engineering and medical electronics. So once you find that motivation, then it is important to learn the fundamentals. So without the fundamental knowledge of what is happening in the respective area, it is really difficult to proceed forward. So learn the fundamentals, and this is one thing that my friends and I share the common idea: study to learn a concept or learn a technique or technology in that particular field, and not for grades. Because I know during my bachelor's and during my studies, I have seen a lot of people, and sometimes even myself, we just study in order to just get grades and be done with certain courses or certain subjects. But that might not be very effective, because once you are studying with interest, and if you are studying with real interest for technology and that area of biomedical engineering or medicine, then you will automatically understand what is happening in whatever you're studying. And if you know things from the fundamentals, then exams are just replicating or just transferring your knowledge to a paper or computer or whatever. So at the end of the day, if you study in order to understand things out of interest, then the outcome is of course going to be good grades. So but never do the other way. Never study to get good grades, and that works out, but in the end it is not very effective. And also during your bachelor's, learn some kind of programming language. I pretty much everyone, or pretty much on average everyone, starts with MATLAB during their bachelor's, and maybe C++, depending on the course. So in medical electronics, I believe medical electronics and biomedical engineers, we start with MATLAB and maybe some other or MATLAB and some other tools which are used for signal processing, but also study other languages such as Python, because Python is really useful these days. Every institute or every university uses MATLAB in order for research or in order to do certain tasks. But once you're outside of university, then in the industry level, people prefer to use C++ or Python, and very few use MATLAB. So even if you are using MATLAB during your bachelor's or undergraduate studies, it is always really advantageous to have some other programming language in hand, either C++ or Python. So always learn a programming language, and always be up to date with whatever is happening in the industry. So for example, we learn certain things from textbook during our studies, but those are fundamentals of, like, the really basic fundamentals of whatever you are studying, medical electronics or biomedical engineering or even mechanics. So these fundamentals are there to help you understand concepts, but those are those are a bit not in par with what is happening in the real world. So in the real world, the advancements are really way ahead. So if you are learning something, simultaneously also see what is the practical application of it and where the technology is being used. So once you learn something and simultaneously check where it is being used, then you will get to understand the more practical aspect of what you're learning, and also get to know what companies are working on or what research industries are working on in that area of field. And also, if possible, during your bachelor, excuse me, during your bachelor's, if you have enough time, then you could also apply for internships and other form of practical work, because studying from books up to a certain point will help you get all the knowledge and all the fundamentals that you need in order to understand something. But practical work is also equally important. That's why you have lab sessions during your studies, and that is also very useful. So you get to know how to apply your knowledge in practice. And when you are doing internship in certain industries, then you also get to know from the industry point of view how their workflow is in order to create a medical device or an assistive device. And finally, the most important thing, or equally important thing, is in order to have a huge network of people from that particular area or from a multidisciplinary area. Because, so for example, if you are a electronics engineer or if you study medical electronics, then you have a very good knowledge about all the electronic circuits and sensors and anything related to electronics. But when you do a project, it is always a collaboration between scientists or people from various scientific communities. So you collaborate with people from say depends on the project, but in general, there will be a software development group, and there will be a hardware development group, and there will be a management group. So it's always good to network with people who are in this line of interest, and it's always better to grow this network as you go forward, so that you get to know more of what is happening in other fields, and also be in contact with people in order to get more opportunities in the future. So once you're done with your bachelor's, you could also pursue further to master's, but there are certain reasons which are very, how do I put it? So for example, people have this misconception that if we do a master's degree, then we will automatically get a really good job. Um, yeah, that is true in a way, but it is not true in all the cases, because it depends on several factors. So for example, if you do a master's, there are certain reasons for you to do a master's. So you either acquire domain specialization, which is very in-depth knowledge about what do you want to study. So for example, if I am studying medical imaging related techniques and technologies here in my master's, so I acquire that domain specific knowledge apart from the fundamental knowledge. So that is one reason, one very important reasons in order to pursue masters. So if you want really in-depth knowledge about one particular field, and you also actually study other than this main area, you also have to study other um, multidisciplinary fields in order to better understand the practical application side of it. And another reason to do masters is if you're interested in research and development. So most of the studies related to masters will be research oriented, and by that research oriented work, you also get to collaborate with institutes and different industries. So this collaboration actually helps you to see more on how the workflow of actually meeting an end product or a final device is. So all this in-depth knowledge, when you do some practical work with companies or institutes or industry, then it is actually put into practical use. So during your masters, you will actually get, I mean, pretty much every university will have some kind of MOU with other industries or other research centers. So you will get hands-on experience during this. And the final one is your career opportunity. So doing a master's will, of course, or not of course, but gives you a chance to go a step ahead or a few steps ahead in your career. But it also depends on the skill sets you develop during your studies. So doing masters without developing any new skill set will not automatically guarantee you that you will get a better job or you will go to a better rank. But provided you develop the necessary skills and also necessary practical experience, then for sure you can always improve the opportunities you get and always have better chance. So this is just a small information about how masters in Germany usually works. So most of the master programs in Germany is research oriented, at least with the programs which are in the part of engineering. And the universities provide free education, but when we say free education, it is not exactly free, but there is some semester fee we have to pay, but it is comparatively very less. So that is one really good advantage compared to other countries. And also most of the industry leading or leaders in the industries are in Germany. So for example, in medical engineering, so we have Siemens, we have Draeger, we have Roche. and we have various brain lab. We have several industry leaders here in Germany. So all the research which is currently in in development, or which is in the phase of development, happens in Germany, at least most of the research. So you always get to know what is happening, and there is always constant opportunity. And there's also access to other countries in the European Union if you are in Germany, and you could always apply for internships or apply for masters. And there's always this close connectivity to other countries if you're in Germany. So, and you also get international experience when you're studying not only in Germany but anywhere outside your home country. For us it is India. So you get to meet a lot of people, because when we are around the same people, we tend to have this narrow focus. But when we meet different people from different countries and from diverse backgrounds, our perspective on things start to change. So that is also an advantage when you're doing masters. And these are just some uh, points which I would like to share. And in the end, you have to understand that when we do masters, it is mainly to get a more in-depth knowledge and more development of your skills, rather than the focus to just get a better job. There are other ways also to get a better job, so it depends on how we think. So once you are you have determined that maybe, okay, I want to do a master's, this is just information which I personally wanted to share. So if you are interested in masters in Germany, then you could always visit the website of DAD. You can just Google it, and they have the international master's program options where you can just go filter what area of field you want to study. Or if you don't know, you could just search biomedical engineering, and all the universities which provide this course will appear in the website, and you can just go through each of the universities and check the links on what is the requirement for admission, which university offers which program, and how long is this master's program, 2 years or 1 year. So you get to see all this option in the website. And apart from this website, there are also other websites, but this is a bit more official, so you could see this. And sometimes I not get requests, but most of my friends they ask me which is the best university in Germany to do masters. And I always hear this, and I always see this in other groups also, admission groups. Personally, I would not per yeah personally I would say there is no one best university, because each university focuses on their own research in that particular field. So you cannot actually compare universities saying, oh, this is the best one, this is not that so good. But so if you have a focus, if you have a field of interest that you would really like to explore, and you would really like to develop your skills in, then you could simply search which university is providing that particular program, or which university is dealing with that line of research. And you could simply go through the requirements and see how you can apply and what research group they are working. And because every university which does or who does research, they are always in constant collaboration with industry partners. So you have multiple. So for example, in my university, they are in collaboration with Siemens, and there is a medical imaging company here in the city itself. So there are multiple collaborations always with industries and institutes. So once you know that particular field of research, or once you're interested in that particular field of research, then you can just see which university is dealing with that. So bottom line, there is no one best university. It's always each for their own. And learning German, for at least Germany. So learning the local language when you're dealing with European countries is always really useful, because no, even if the program of study is in English, so the local language is what will help you in order to manage your basic day-to-day life, going outside, going to bank, or doing any other work outside of university. You need to know the local language. So learning the local language is always helpful in order to integrate your life better in the city which you are living, or in the country which you are living. So anyone who has an idea of coming to Germany, I would suggest that you learn some level of German at least. So there are levels of A1, A2, B1, B2 up to C2. So I would at least say learn till A2, or at least A2, so that you at least know what people are saying, like the basic stuff. And this is not only with Germany, even if you are planning to go to any other country in Europe, it is always better to learn the national language of that country. So, and all as equally important, but not up to that level of importance, but still it is important to know the culture and the traditions of the country you're visiting, because what you do or what we do in our daily life back in India, certain aspects might appear rude or might appear not so polite to people in other countries, and it goes the other way also. Who do certain people who have certain habits in other countries might appear rude to us. So it's always good to understand what is the tradition and what is the culture of the other countries in order to better integrate it. And that is also one of the important reasons, or not reasons, one is also the important thing to keep in mind when you're applying for masters. So next, I would like to just talk about my university, which is Otto von Guericke University at Magdeburg, and it's in Germany. So we have also 15 international master courses, which some of them are in English, some of them are in German, and these courses are also most of them are research oriented. It depends on what course you choose. So I study medical systems engineering, which is related to biomedical engineering, and our university focuses on various aspects of medical engineering, such as medical imaging, radiation physics, biomechanics, and computer aided application of computer science in medicine. And also there's one more, yeah, neuroscience is a really huge part of our university. So all this are under medical systems engineering, or comes under the study master course medical systems engineering. And we also have several research labs and research campuses. So I used to work in one of the research campus, where we have MRI, we have CT, we have C-arm, and we have I pretty much. So if you know about MR systems, then most MR systems that we use in hospitals and hospitals and institutes will be 1.5 Tesla or to the max 3 Tesla MR systems. And we actually have a 7 Tesla MR system here at the university. And it is a super high resolution system where we basically use it for research, mostly for research. And there are very few 7 Tesla systems in the world. I think few in the US and few here in Europe. And one of this is in Magdeburg here in Germany. So we also have connections with, or relate, yeah, understanding, how you call MOU, with various industry leaders. Yeah. So the research campus which I used to work in, they were in close contact with Siemens, and also with here companies which are in Germany. Some of them are not international, but they are really good companies in terms of developing medical software and applications. And there's also always opportunities for postgraduate studies when you're doing masters. And also in my university, there is also postgraduate studies. So now to talk about medical imaging applications. So this is where my specialization comes in. So I specialize only in medical imaging, and there are various subcategories in medical imaging. So you have your medical physics, radiation and medical physics, computer tomography, magnetic resonance imaging, medical visualization, computer aided surgeries. I left out ultrasound imaging because I do not study ultrasound imaging. I mostly concentrate on CT and MRI and other techniques. So these are some of the technologies and techniques that I study in my course of medical systems engineering. So I would be sharing my experience and knowledge with you regarding these particular fields. And each field has its own set of required skills and development requirements. So we will be going through each of this in order to understand what is happening in each area and what is required of engineers in order to contribute to this area. So first, radiation physics or medical physics. So radiation physics basically deals with any kind of ionizing radiations in order to develop therapeutic or diagnostic applications. So diagnostic application starts with X-ray imaging or radiography. So X-ray imaging is radiography is 2D imaging where we use X-ray and we project these X-rays to our body in order to visualize most structures inside the body, because X-rays are not very good at handling soft tissues or soft organs, because the X-rays attenuate very well with organs with high atomic number. So any dense organs we would be able to see using X-ray projections. So bones, mostly bones and cartilages and other dense structures. So these radiography techniques are always useful to image structures inside our body which are very dense. So that's why we always use X-ray images in order to diagnose any fracture or in order to diagnose trauma, such as accidents or certain injuries. So this is a part of radiation physics or medical physics that deals with ionizing radiation. And there is also fluoroscopy, which is also the use of X-ray, but we get to see real-time images in terms of temporal resolution. Because in fluoroscopy, if you have seen a C-arm system, which basically uses again an X-ray source and detectors on the other side. So a C-arm system, basically you can view or image objects inside or image structures inside the body in real time. So X-ray fluoroscopy is also of great use in basic diagnostic of so for example, if we want in catheter, any not intraoperative but any interventional diagnostics. So for example, if there is a heart wall replacement, or if there is a blocked vessel in the heart, and if we need to deploy a stent to the heart, then we use X-ray fluoroscopy initially to examine the degree or the extent of the block, and in order to administer the stent. So for applications in this category, we use X-ray fluoroscopy. And also, apart from this, we also use PET and SPECT, which is positron emission tomography and single photon emission computer tomography. So these imaging modalities use radiopharmaceuticals, which are basically unstable nuclear isotopes. So PET and SPECT uses two different kind of isotopes. One uses gamma emitters, and another uses beta plus, or which is positron emitters. and both work in different ways, but both basically gives us an idea on which part of the cell or which part of the tissue is acting normal and which is acting abnormal. So for example, when we administer a radioisotope into the body with the help of biomarkers, so these markers help these isotopes to attach to one particular tissue or one particular target area and not travel everywhere in the body. So for example, if we want to monitor the activity of thyroid gland, so you administer the particular biomarker and the radioisotope or radiopharmaceutical, and once it reaches thyroid, uh, there are systems like how we have systems for X-ray, radiography. We also have systems for PET and SPECT. So they basically have detectors which have scintillation crystals, and they have also medical electronics part. So for example, an ADC, a readout circuit, which are basically used to sample your signals which we acquire. So these electronic circuits are used to collect the data or collect the signal or the radiation which is emitted from this particular target, which is for us is thyroid. And these data or signals are used to form a color map, so which is basically what you see in the slide. So how this works is, if you have a cell or a tissue which is hyperactive, in case of cancerous tissues which multiplies very fast and consume more energies and other vital um, chemicals, so these tissues have higher activities. So because of higher activity, they consume also more of the radiopharmaceutical. Therefore, we get more radiation from this particular area of the tissue compared to other particular areas. So these radiation levels are monitored or collected by the detector and converted into signals. And these signals are further converted into medical or images, which you can use for diagnostic. That's what basically happens in PET and SPECT. So these two are diagnostic modalities when it comes to radiation physics. And there's also therapeutic, which is radiation therapy. And the image you see on the slide under radiation therapy, it's basically gamma knife. So there are other modalities also, such as LINAC, which are linear accelerators. So here we do not use imaging, we do not for imaging application, but rather for therapeutic application. We also use high intensity X-rays in radiation therapy. So if you have after imaging, and if the doctors find an abnormality in the region which you are imaging, so this abnormality, for example, say is a mass or a cancer, so this cancerous growth can be shrunk down to a smaller area before surgery. So this can be done using radiation therapy, such as high intensity X-rays, LINACs, or gamma knife, where you project very high intensity X-rays, which are gammas, and from various angles to that point in the target. The reason why we choose to project from various different angles is because when we project high intensity X-rays from one particular angle, so the path through which the X-ray travels, it attenuates and it affects all this tissue in that path. So if we keep on applying X-rays in one particular degree of, not degree of freedom, but one particular path, then you ionize all the tissues. We keep on ionizing all the tissues in this path, and that might lead to heating and maybe other stochastic effects in terms of radiation in tissues. So that's the reason we apply radiation from various different points, as you can see in the image. So we use radiation also for therapy, and it also comes under medical imaging and radiation physics, because it at the end of the day deals with radiation sources. And in order to monitor this activity, you have to again use imaging modalities to see how much the tumor or the mass has shrunk down to. So this is also an important part in medical imaging. And the only disadvantage, or comparatively to other areas, is that we use ionizing radiation and sources which produce ionizing radiation. In certain ways, they are harmful, but only if proper precautions are not being taken. So, for example, I worked as a medical engineer in radiation department of hospital, and we use protective shielding such as lead aprons and lead shieldings whenever we are using fluoroscopy or radiography, which are basically 2D projection X-rays, or even in computer tomography. So whenever we use proper protection and proper shielding from radiation, it is always avoidable the unnecessary or the extra radiation dose to the patient or to the doctor. But that is uh, a single drawback of the technology in terms of patient care. So there are certain numbers or certain annual dose limits that you're allowed to receive, and it changes from it differs from patients and also to radiographers. So after this particular limit has reached, so radiographers are not supposed to work anymore if they reach that limits, and we can also monitor this using dosimeters. So that is the one small disadvantage with respect to radiation physics. But the advantage is outweighs the disadvantages. So that's why we keep on using certain technologies. So here you can see combination of different modalities. So for example, the image on the right is a PET image, or data acquired from PET scans, which shows increased activity in a region of the body. And this color map can be mapped to other imaging modalities. So for example, if we take a CT scan of the patient before monitoring the activity, and we have the data, and then we use a PET scan to monitor the activity and collect the data, you can actually fuse these two data into a single image in order to better localize or better visualize in which anatomical region is this activity higher, and is it affecting certain organs or not. There are also not structures, there are also technology where you have both a CT scan and a PET scan in a same scanner. So that's what is a PET CT or CT PET. And these scanners are more useful in order to get such images where we can better visualize an activity, and you do not only see the physiology of the structures. And one more thing related to radiation physics is risk assessment and biokinetics. So basically, when I told you that we use biomarkers in order to administer biomarkers, we need to know how the biomarkers would travel and to which organs the markers travel and at what time do they exit. And because at the end of the day, scientists are dealing with radiation sources, unstable radiation sources, which produce decays. So it is important to know or to estimate how long this decay will continue and how much activity of radiation will be there at the end of the treatment, at the beginning of the treatment. So this is done using biokinetic modeling. So where we can basically estimate which organs get these biomarkers, and which target uh, get the biomarker, or how the biomarker reaches the target. So this calculation is done using biokinetic modeling. That is also a field of study in medical imaging and radiation physics. But moving on from these modalities, there is also computer tomography. Excuse me. Yeah, so we dealt with 2D projections and 2D imaging in X-rays or radiography. But in computer tomography, we use the same principles of X-ray radiography, but we can acquire 3D image slices. So as you can see, if you have not seen a computer tomography system in person, the hardware kind of looks like how you see here in the slide on the left image. So you have a 360-degree gantry, and it has an X-ray source and a row of detectors or ring of detectors, and the X-ray source and the detector rotate 360-degree in order to get a complete slice, and the patient moves inside the gantry while the gantry or the system X-ray detector setup is rotating in order to get multiple slices of the target area. So computer tomography uses principles of X-rays such as attenuation is a really important thing, because computer tomography images are acquired based on Hounsfield units, which is basically how much the tissue attenuates X-rays and how much it does not attenuate. And this collected signals or collected signals are converted into pixel values using Hounsfield units, and then we process these values into images. But computer tomography also needs hardware development. So medical electronics, again, everything comes back to hardware and software. So everything from the patient table, because there are a lot of add-ons or like a lot of technology that also goes into the patient table uh, in order to say assess the respiratory motion. You could use sensors in the tables to monitor respiratory motion, and this could be used in order to cancel motion artifacts. So when the patient is being imaged, if the patient is moving, and if the organ, say a particular organ or lungs, you have a movement in the lungs, this movement could, it's a possibility that it could affect your image which you're acquiring. So this could be canceled out using certain technologies, and there is one particular technology where they use sensors in the patient table in order to get the respiratory rate, and this is used to cancel the movement in images. So there's always hardware development in patient tables, and main hardwares are in the gantry or in the CT system itself, where you have your X-ray sources and you have your entire rotating system and also your detectors. So X-ray detectors are something which is always been or always are in constant development. So your X-ray detector has three to four basic or principal parts. So one is a scintillation material, which, so whenever we project X-rays from the source to the object, after the X-rays pass the object or after attenuation, these attenuated or the left out X-rays are collected by the detector, and X-rays are converted into visible light using the scintillation materials. There are various scintillation materials that are in use. I think cesium iodide is one of the commonly used, and there are different variation of scintillation materials. And these materials convert your X-rays into visible light. So that is one. And visible light is converted into signals using photodiodes and other electronics. So once these signals are once these X-rays and visible lights are converted into signal, these signals are used or read out using readout circuits with ADCs and different electronics which goes into reading signals and processing signals. So that's why electronic development or hardware development is a big part of computer tomography. It's always in development in order to reduce the scan time, because since we are dealing with radiation sources, if we have more or if we have larger scan times, then you are exposing the patient to more radiation. So the field of research that goes on in computer tomography is how do we image faster, or how do we image an object with less radiation and more sensitive detectors. So this is always a constant research area, the field of development. So hardware development is really important in computer tomography, and as equally important as hardware is software. So once you acquire this data, once we manage to get a data, we have to process it, and in order to visualize it, we need to convert it into images. So any computer tomography technique basically gets a sinogram. What we call a sinogram is, so when you have X-ray sources from one point to other, it crosses a body. And when you have 360-degree imaging, the data you get is a sinogram of your object. And this sinogram is converted into images using radon transform, which is a mathematical principle which involves Fourier transform. And this radon transform and inverse radon transform are used to acquire images from the signals or from the sinogram. So that is one part, and that's the other part. And there's also always simulation in computer tomography or radiation physics. So in simulation, what we basically do is, if we know that we are developing a new system which uses a certain structure of hardware or certain software, then this system can be designed in certain softwares or using certain tools. So for example, there is Gate, which is one of open source toolkit or software. And there's also Geant 4, Geant 4, Geant 4. So these are simulation softwares in radiation or medical physics, which we can use to create structures. So for example, in the image you can see here, the circular structure is a detector setup, X-ray or CT detector setup, and we can also create phantoms and objects using GAN4 or Gate. And these, if you see this now, you could see that the movement of the lungs or movement of the rib cage and the lungs, and this can be simulated, and you could also simulate X-ray photons, and these simulation results can be saved in terms of just text files or JSON files, and these files can be used to convert the acquired data into images. So we can do various simulations using such open source softwares in order to acquire images or in order to test a system that is being in development. So apart from this, there's also different kind of artifact reduction techniques in medical imaging of CT. So the one which you see on the left side of the image is actually a motion artifact. So the patient under the system, if they move, so for example, this is a head. So when the patient moves the head, your imaging system, since it is always in constant motion, your detectors and the X-rays, so once you do a slight movement and come back to the original position, since this motion has already passed, your signal acquired or your image looks like this because the patient moved. And there are also other kind of artifacts. So for example, the one in the center is we call there's beam hardening, and it's also the spikes. We call there's radiation spikes. This also occurs due to either energy difference in the radiation source, or whenever there's also an implant in the body, it attenuates very highly because metals have very high atomic number. And because of that, there's also spoke artifact that could occur. And the image in the right side is image of a ring artifact. So these also occur because of geometric problems and also different other outside effects, or how do you call it? Yeah, outside effects. So there are these artifacts occur not frequently, but most of the times, and there are also imaging techniques which are used to correct these motion artifacts and various other artifacts. And equally, you can also develop hardwares in order to avoid certain artifacts, like how I told you, like the motion artifact. But in terms of head movement, we always use a head resting headrest. It's called a headrest. So headrest, so that the patient doesn't move much. So these objects which are used inside the CT system, they can be developed, because if these objects also have very high atomic number, then they also attenuate X-rays and you get very bad images. So you can also develop these hardwares which are radio opaque, which basically passes radiation and does not attenuate radiation. So that is also one important part of computer tomography when it comes to CT. And with respect to imaging, there's always reconstruction of images, and also like how you see now the artifacts. We could also remove artifacts. And moving on, before that, I would like to, this is the simulation open source software which you can download or install in Linux, Mac, or Windows, any OS. So you could go and visit the website of opengatecollaboration.org in order to, if you're interested in simulations, or if you're new to simulation and if you want to try how this works, you could check out the website of Gate, or you could also check out the website of Gian4. So basically, they are kind of the same, but it uses just different modules. So an overview of what you can do with simulation software is, you can basically construct a detector, you can assign scintillation material, you can assign scintillation material, you can assign electronics, you can assign the material of the objects which you're creating, which we call geometries. And these geometries can also have properties such as atomic number, mass, and everything, so that they do not attenuate X-ray, or they attenuate X-ray based on the principle, based on your application. And you can also produce, so that one was geometry, and the other is you can also produce X-ray interactions in simulations. So you could produce fan beam X-rays, cone beam X-rays. You can adjust the X-ray intensity, or you can provide X-ray intensity ranges, and you can also monitor different types of X-ray interactions, such as Compton scattering, Rayleigh effect, and other types of X-ray interaction. And it is not only X-rays. You could also simulate gamma radiation. Depends on application. You can do various simulations using Gate and Gian4. So these are some of the open source toolkits which you can install, and there are some YouTube videos which are also useful to guide people who are new to Gate and Gian4 on how to use it. So moving from computer tomography to other modalities, we have magnetic resonance imaging. So in terms of magnetic resonance imaging, it also has hardware development and software and image processing parts. So the advantage over CT is that MRI does not use any radiation sources or ionizing radiation. Rather, MRI uses, in a way, they use magnets and electromagnetic and electrical pulses, or to be more precise, RF signals, in order to get images. So basically how an MR system works is, we have a very huge magnet which produces homogeneous magnetic field, meaning the field does not change. The strength of the field remains the same. And whenever an object, so in our tissues, there are hydrogen atoms, and hydrogen atoms have protons, and these protons are randomly oriented in different directions. And whenever we place this tissue, or whenever we place a human in this constant magnetic fields, these protons tend to align perpendicular to the magnetic field. So once they are in perpendicular to the magnetic field, we could also use additional RF signals, or we call it gradients. So these different gradient coils are in different directions to get an orientation. And once we send RF signals from the coils to the body, the protons start to spin in the direction based on the amplitude of your signal. And these pins, when you turn off the RF pulse, they actually come back to their original position. So this excitation of spin and returning back to original position, it produces a signal, and these RF signals are collected by receiver coils, and these signals are further processed to get images. That is like the basic understanding or basic principle of how a MR system works. So as you can understand from what I said, that there's a lot of hardware involved in MR systems development. So similar to CT, you also have a patient table where the patient is placed. You can always do developments in patient table, where similar to computer tomography, here you can use also various sensors in order to reduce or cancel out motion artifacts. Example, respiration rate is most commonly canceled out motion artifact, and you can integrate such electronics and sensors into the table. And nowadays there are also intraoperative additional devices which you can add to the table, but that is another part of MRI. So, and there's also development of hardware where you have RF coil and RF coil design, and you have design and development related to magnets basically, and you also have receiver coils. So there's a lot of coils, different coils, gradient coils, receiver coils, and other electronics which are used to control the strength of these pulses which we develop. So that is hardware part of magnetic resonance imaging. And in terms of the how we acquire images, so we basically use pulse sequences, and these pulse sequences are generated by switching on and off these coils. So for example, an initial RF pulse will excite your protons in the body, and then when we switch back and forth, not back and forth, when we switch different strengths of gradient coils, we get different kind of excitations in our proton, and these different excitations will give different signals which we can view as an image. And this pulse sequence development is done using certain software. So one of the software tools which I learned was PulseSec, which you can see from the slide, PULSEQ. So that is an open source tool which you can use for pulse sequence development, and we can do it in MATLAB and Python. And this is basically used to develop different pulse sequence in order to get different kind of images, because each pulse sequence produce different images in terms of contrast. So the basic principle is that there are different types of relaxation, which is T1 relaxation and T2 relaxation, that happens when you excite your protons. So depending on the pulse sequences, we get different kind of relaxation. We are able to observe different kind of relaxation, and we get different kind of images. So why am I concentrating more on pulses is because it is kind of the heart of MRI, because if we use different pulse sequences, we are able to observe different contrast or obtain different contrast in imaging. And MR image is very good. MRI as a modality is very good for imaging soft tissues, because soft tissues range from different sensitivities, and each tissue has its own property or own physics. And when we are able to notice this T1 and T2 of each tissue, then we are able to differentiate each tissue based on this contrast, because they have different relaxation times. So for example, water and fat have different T1 and T2. So if we are able to develop pulse sequences that are able to differentiate water and fat, then you could easily see if there is water where there is not supposed to be water inside any organ. So for example, lungs or any organ which you're imaging. And once we are done with pulse sequencing, then we have image reconstruction part in MRI. So the signals we acquire using pulse sequence or pulse prototyping from the receiver coil, these signals are stored in a K space. In MR imaging, we call it K space, which is basically you have different frequency and phase information in kind of a matrix. So this K space is inverse Fourier transformed, and we can apply multiple operation in order to get the image space. So that is how we do image reconstruction in MRI. But that is basically how we do image reconstruction in MRI, but there are more advanced techniques in order depending on the pulse sequence. So an example of one pulse sequence here is diffusion weighted imaging pulse sequence, which I show here. And this is just, I won't go too much in depth because this on its own is a very deep, how do I say, you need to know a lot of fundamentals in order to understand what is happening. But just to give an idea, so for example, when we apply an RF pulse and we choose our slice that is to be imaged, this excitation can be further, how do I say it? Yeah, you can image one particular part of your slice and excite the other particular part of the slice in order to view the blood flow or view the diffusion of fluid in your tissue. So that is the application of diffusion weighted imaging. And this is how a pulse sequence in general looks like. But in order to understand more of pulse sequence, we have to go too much in depth into sequence prototyping and the physics behind it. But just to give you an idea, this is how a scheme of pulse sequence looks like. And we move on from magnetic MRI or magnetic resonance imaging to medical visualization, because once we collect the 3D data from, say, CT or MRI, so these data are basically slices, right? So we have different slices, and each slice has voxels, so which is basically pixels in 3D, volume pixel or pixel volumes. So these slices, which we acquired using CT or MR, these 3D data can be used for diagnostics. That's where medical diagnostics always comes in, right? We use this data in order to diagnose a condition. So whenever we have a 3D data, we can use this data to segment certain parts. So for in this image, if you see, there is some mass or a tumor or a cancer, but in general a mass. So if we want to segment out this mass and see how big it is and how is the structure and physiology of this mass, so we can use the slices acquired from CT or MRI, use these slices, and there are certain segmentation softwares or toolkits which you can use, which are also open source. So for example, ITK is one of the open source toolkit. If you can just Google ITK, you will find it. So which is most widely used for image segmentation, and there are also other toolkits which are useful for image segmentation. So using these toolkits, we can obtain or we can extract certain information from these 3D slices, and these informations can be modeled or 3D modeled using other additional softwares. So Mavis Lab is also an open source toolkit or software for visualization of objects. So once we acquire this region which we want to visualize, once we have the data, then we can use this data to visualize the object, as you can see in the screen, using this Mavis Lab or other softwares which different people use. So once we have this image, or once we have this model of how this structure looks in 3D, then we can use this specific structure or model for various other purposes. So for example, if you know that there is a tumor of certain size, and if you can able to visualize it using 3D modeling, then you can use this visualization in order to perform surgeries or in order to further diagnose the condition. So this is one interesting part of medical imaging that I came across during my studies. And this can be visualized using softwares and other toolkits. So whenever you have a 3D model from your scan data, you can visualize internal structures such as blood vessels and other organs, and we can color code these blood vessels, and we can see how close this blood vessel is close to an important organ or an important target, and how big or how is the extent of the growth of this tumor or mass. So you can always get a better visualization of your organ or your tissue of interest in order to do further diagnostics or further treatment. So this is a really interesting part of medical imaging which I personally liked during my studies. And these once we have acquired these 3D models or 3D volumes, the next is computer aided surgeries, where we use these 3D modules and 3D volumes in order to perform surgeries or while during surgeries. So one of the aspect of computer aided surgeries is tracking and navigation. So for example, when we are using a surgical instrument which is used to, so for example, if we are using it for resection, which is basically cutting of an organ or a structure using equipment. So as a physician, I cannot say we, but a physician knows the anatomy of the or the physiology of the organ. So where it is located and where are the blood vessels, and if I cut in this particular area, there will be some blood vessels here. So physicians know to some extent about this, but physicians do not know if there is any abnormality behind that. So these 3D volumes which we acquired in from our CT data and converted into 3D models, these models can be used to visualize certain risk structures. So, and also these equipments which are used to cut or which are used to resect the organs, they can be tracked using certain systems. So if you see in the slide on the left side, you have an infrared system which emits infrared source, and it also has an infrared camera. And these infrared systems, when they emit infrared source, there are certain structures attached to your instrument, and these structures will reflect back the infrared light which is captured by the camera. And with this setup, you can track your instrument, how it is moving in the object or when you are using. So this is one type of tracking system which people or which scientists use in order to track instruments. And why do we need to track instrument is because once we have this 3D model, we can use computer software to integrate this tracking measurement and the 3D object in order to visualize how this instrument is going through the organ. So in the middle image, you can see that it is a liver resection plan, and the pink line which is going through the liver is the resection plane. So that is where the surgeon is supposed to operate and cut the liver on. And in this plane, you can see the blood vessels. So different blood vessels are color coded when we are modeling in order to differentiate it. And there are certain places where it is yellow. So these places are the places where the instrument could possibly accidentally or possibly hit. So this gives a better visualization for surgeons to understand the risk behind it. So one small story which I would like to share is, so I had a relative who had pancreatic and liver cancer. So the surgeons basically had to remove the part of the tumor from the pancreas and liver, and it was a very serious surgery. So they knew the structures, they knew the liver, they knew the pancreas and the structures behind it. And so they were resecting like a normal procedure for normal surgery. But there was a blood vessel in the liver which was not supposed to be there. So everyone does not have the same anatomy and everyone does not have the same structures in their organs. So they found a blood vessel which was not supposed to be there, and they accidentally resected the blood vessel during this surgery. And because of this, there was a lot of blood loss, and it was a very critical condition. But fortunately, they were able to correct this. So visualization models, like I mentioned before, and navigation tools could be used to avoid these kind of situations where you accidentally resect or accidentally do certain actions which could be avoided. So this plays a really important part in medical visualization and intraoperative surgery when you have visualization models. And another part of computer assisted surgeries is virtual reality and augmented reality applications. So virtual reality mostly deals with simulations. So where we use this 3D data. So for example, if we have different CT scan, different MRI scans, we can use this 3D data in order to develop a simulation tool. So for example, doctors or resident surgeons, new doctors, they train on surgeries, they train on certain applications or certain procedures using the simulation toolkit. So there are simulations where you can perform surgery on a graphical patient, and you can actually move the organs and you can resect through organs. So when we have these 3D models, which are from real-time data, these 3D models can be used in the simulation because it is more realistic data. So that is the actual data you might be working on on a patient. So that is the VR application of imaging and 3D modeling in computer assisted surgeries. And there is also augmented reality, where we use this 3D data along with other augmented reality applications. So one of the application which is in research and development in our university is, so we have CT scans, and we have CT scan 3D data as slices, like it's multiple slices. So during surgeries or intraoperatively, if you are operating on a certain organ and if you have images, you always have a assistant, or like a doctor has a associate, excuse me. So these associate, they either touch the screen or touch the object in order to navigate through these images, or they always physically touch some remote or some button in order to view the images. So a professor of mine in our department, or in computer science department in biomedical, they developed an application where you have sensors on your gloves, and these sensors are basically tracked by a camera, and these camera and sensor setup is used. So for example, if we have a hand and if we do certain gestures, so for example, move left, move right, or back and forth, we can actually change the slides or slice on the computer. So for example, uh, pushing back and pushing front and back can zoom in and zoom out of in the slice, and movement of hand could actually help to change slice. So that is a really cool technique they are developing here. So that comes under augmented reality. So that is one part of medical imaging. And this is just a general setup which explains, just to give you an overview, not too much in depth. So equipment which is used in the robotic arm has some sensors which the camera can track, the tracking device. And when this operating device is moving on the patient, the camera tracks this movement. And we have our scan data which was done before the imaging, and we can use software to mark the crosshair and how the instrument is tracking. This is just to give you an overview of what I said before. So we can use this in order to know in real time where the instrument is moving without actually seeing inside the object. And coming from those principles to some of the projects which I worked based on some of these principles. So I won't go too much in depth because some of them are ongoing projects. So one project which I worked on was tracking of objects movement in order to reduce movement artifacts in CT systems or C-arm systems. So that was one of the projects which I worked. And as you can see, there is a human skull which was imaged, and the black color object you see is a visual marker. And this visual marker is tracked by this camera, which is a white box which you can see. And when the object is moved or displaced, this displacement is recorded from the marker and the camera. And this movement is actually recorded in a separate software in the system. And this data can be collected and processed in MATLAB in order to see how the object is moving. And at the same time, when the from the tracking device, and we compare the degree of movement which is recorded in the CT system, and we use these movements to reduce or cancel out motion artifacts. So that was one of the projects, just an overview. And another project which I recently completed was there is a CT system which is currently being under development in the university. And so my part was to develop or to evaluate the CT design. And in order to evaluate CT design, we cannot always use radiation sources and keep on exposing stuff to radiation, because it is unwanted use of energy and also radiation risks. So I use GIANT4, and I use GIANT4 in order to create the structure of the CT detector which is being developed. And it was actually a project of one of my seniors in the department, and I continue the project to evaluate the structures. And so in this, I basically designed the detector which you see here, which is in the red cone. Yeah. So this detector has scintillation crystals, which is blue in color. And I also project radiation, which is fan beam X-rays. And if you see the image, so you can see that the radiation source moves from each point. So it depends on our project, but yeah, I will not go too much in depth because it is an ongoing project, but just to give you an overall idea. So this is done using GIANT4. And once the simulation is done, we collect the data and we use this data in MATLAB for reconstruction. So for example, if you see, the radiation source is fan beam, and it passes through the objects, which are the blue color cylindrical objects. And on the opposite side was the detector. And these detector objects collect the data, attenuation data basically, and saved in text file. And these text files are read in MATLAB. And we have to understand the geometry in order to reconstruct the image. And so this is a reconstruction which I did. And you can see that the different cylinders are visualized or are visible in the reconstructed image. And also there are certain artifacts, such as streak artifact. Sometimes it happens because the object, so it's a different not motion artifact, so kind of artifact. So this was one of the projects which I did, which I completed a bit recently. And now I am working on my master thesis, which is based on MR image reconstruction. And we know that MR imaging takes around 2 to 3 hours, or sometimes also 4 hours, depending on the type of imaging we perform. So how do we reduce this scan time is what is it is still in development, and there are also developments being done. So that is the area where I am working in currently. And the basic idea is that instead of collecting all the data points in the K-space, which I mentioned earlier, so we collect only certain or half of them, or like randomly. And by doing this, we reduce scan time. And when we do collect the data randomly, we can actually reconstruct the proper image from this less data, which is sparse data. So this sparse data can be used to reconstruct images. And there are several different techniques. This is just to give you an idea, because if we go in depth, that is a session on its own. So this is one of the things which I'm working on. And I also use normal iterative reconstruction techniques and also deep learning techniques, which I am fairly new to. So to give you an idea of all the open source softwares which are useful for image processing. So this is one of an open source app. It is a free app on online Android, and it is called KSPAP, from which you can see from the image, KSPAPP. So what it basically allows users to do is the top half of the app you can see is a K space, and you can actually change the amount of K space that you can use or you can visualize, and you can change this to see how data collection in K space affects your image quality. So if you see on the left, you only have the center of the K space, which is usually low frequency information and phase information, which we collected. And this center will give you image, but not detailed image. If you have very less information, then you have very less information in image. So in the middle, you can see that we move away from the center, which also have some high frequency information, and you have a better image. And when we move further away, when we have 80 to 90% of the K space, then we have a very good image in terms of resolution and contrast. So this is a simple app which you can use or download from Play Store, Google Play Store. In Android, I'm not sure whether it's available in iOS, but in Android, you can check it out. And you can better understand how K-space relates to image data. And this is one of the open source tools. And other open source tools, I am pretty sure you know about MATLAB. And MATLAB is most widely used in terms of institutions and universities for image processing, signal processing, and various other tasks. But we now talk about image processing. So it is very efficient or effective to use MATLAB because it basically handles matrices and vectors and arrays in a really good manner. And images at the end of the day are basically matrices. Even if they are 3D slices, they are just different matrices. And MATLAB is very good at handling this. And also, once you are able to handle matrices, then image manipulation and data manipulation is basically going through each of the indices and changing the value in that location or applying certain linear transformation in that location. So it is fairly intuitive. And it's also very good for visualization and plotting. I'm pretty sure if you have done some lab work with MATLAB, then you would know that you can visualize this, how do I call it, phantom. And you can plot intensity profiles. You can see which is the maximum value, minimum value, and all such calculations. So this is basically a Shep-Logan phantom, which you can actually generate in MATLAB using simple function, which I will show later. So for example, you can also use different filtering techniques in order to see which is low frequency information, which are high frequency information. And you can use, these are like basic filters, like low pass filters and band pass filters, which are used to see the information in your image. So which are high frequency, which are low frequency. And so maybe I can show a small program. So for example, I will share my screen with MATLAB. So I hope you can see my screen. So for example, if there is so this is how you basically create. I will not go line by line, but just to give you an idea. So you can use MATLAB in order to create a phantom, and you can use these phantoms to perform various operations. So for example, you could do radon transformation in order to get a sinogram of the object. And sinograms are how CT data are collected. And these sinograms can be used. So for example, if you are able to get a sinogram of 0 to 180 degree, or you can get different projection angles, and you can use these sinograms in order to create the image by performing an inverse radon transform of these collected sinograms. And when you do this, you could get an image and a sinogram. So for example, if I run this program now, it will give a separate output window. So I will not run this, but rather I can show you the output. Yeah, so for example, just a minute. Yeah. So for example, the program which I showed you, we took the same phantom, and we calculated a radon transform, which basically gives you the sinogram, which you can see in the top left corner of the image. And this sinogram can be used in different projection angles or can be changed for different projection angles. And you can observe what happens when you use different projection angles on your data. So if you have very less projection angles, then you get a distorted image. So for example, here, if you use only 0 to 90 degree, you only use that much of your sinogram, then you get a really not attenuated, in a way attenuated image. But if you use 0 to 360 or close to 360 degree, because in CT data you need close to 360 degree data collection in order to obtain better images. So this was the output of the program which I just showed you a glimpse of. So you can basically understand data better in MATLAB using such programs. And this is also one of the things which you can do. And so next is Python for image processing. Python can also be used, and there are various other softwares, libraries, and libraries which you can use in Python. So these are some of the libraries which are used for certain actions, and each library has its own function, and you can find them online and just go through their documentation to see why they are used and how to use as syntax. And similar to MATLAB, you can also do pretty much just a second, like how I showed you in MATLAB, I can also show, I think it's pretty much the same. So for example, you can also use Python programming in order to, I can show you actually the program. So you can use this Python programming and libraries to visualize or read data and collect data. And these data can also be manipulated, and you can also perform various linear actions in this data in order to better understand how your data looks and what actions you can perform using Python and the libraries. So just a minute, I will share the screen with you. So it's actually opening. And since Python is open source, you can find different variations such as Anaconda. You can do from terminal. You can use pycharm, which is also an IDE, which is used for Python programming. So I will now share the screen with you. So for example, this is pycharm, an IDE used for Python programming. And as you can see here, this is how you import libraries. So for example, h5py is a package which you use to read h5 data. So it is one kind of data file. And you can import packages, and you can see documentations on how you can use them to read files. So this is a syntax that is used to read h5 files. So you can check that. And similarly, there are multiple packages that you can use for multiple operations. So for example, this can be used. So this is a program which I used to get the output, which I will show you in the slides. It is a bit time intensive. That's why I will not be running this program. But you can find it actually pretty simple to start from. So for example, that program was used to read h5 files, which is high definition file format. So our MRI data was stored in this file, and these files were read, and then these images were acquired from various coils, so multi-coil data. So we use this k-space information apply inverse Fourier transform and visualize the K space. And we can compress all these coils into one single coil using different algorithms and techniques. And the basic idea or the basic task which I did was, so as you can see on the top right corner, you have an image which is blurred, or it has certain, it's called undersampled image. And this image was iteratively reconstructed using wavelet transformation and soft thresholding, which is a concept. And if you see the bottom image, it is actually free, kind of free from that artifact. So if you run more iterations and if you adjust the threshold, you can actually improve the reconstruction more. So this is just to give you an idea that you could also do image processing in Python. Whatever you do in MATLAB is also possible in Python, provided we know the libraries and the packages which are used for certain tasks. So this is one of the things which I did. And moving on from Python, there's also, I mean, not moving on from Python, but there's another aspect is machine learning, where we use artificial intelligence machine learning to perform image analysis, image segmentation, image classification tasks. And it's a new and exciting area which I found out recently. So for example, we can use chest X-ray classifications, where we use data from labeled data from physicians, and we can feed this data to our machine learning model. And these models classify first train on our data in order to learn what is normal, what is not normal. And once it is trained, then this data is passed through a neural network which was trained. And this network model will be able to observe certain patterns. For example, the starting point will observe low, how do I say it? Very low features such as edges and corners or something like that. And the deeper the model goes, it will be able to extract more features. So for example, a shape of an organ or shape of a mass or something like that. This is just a rough example of how a normal neural network looks like. There are different architectures of neural network, which is a bit in depth. You can just go online and check it out. There are a lot of research papers. And this is just an idea on how the data looks like for the chest X-ray classification. So you have different images, which is under image, and you have different classes, which are the diseases. And if a image or an example has a class, then it means that that image of the patient has this disease. So you feed all this data to your model, and these data are being used to train the model. And once the model is trained, you can feed new test data, and the model will classify whether the new data is under any of these trained classes. So for example, if I cannot show you actual working of a neural network because it takes a long time. And this is an output of one of the examples which I recently did. So for example, if you have an image and this image had a mass and this was trained, not this, but if a neural network was trained on such images, and when you pass an image like this neural network or deep learning model will classify this image based on its learned features, and it will provide an output like you see on the right side of the screen, where it shows that mass probability is 0.95, which means that's a high probability that this organ has a mass in it. And GradCam is just a technique which is used to visualize what the algorithm is looking at when it is working or when it is classifying the model. So it generates a heat map which shows that it classified this image, saying that it has a mass based on this region, and it is fairly correct because the mass is in that region. So machine learning is also a really important and interesting aspect which I came across recently. And you can also do image processing or image classification tasks related to machine learning, related to medical imaging. And this is just a result of accuracy of the model. So for example, radiologists classify certain disease with this much percent accuracy, and your model classifies with this much percent accuracy. And it also gives an idea on how accurate the model is. You don't need to go through everything of this, but just to get an idea. And to wrap this up, an application basically from all these subcategories of medical imaging, what we talked about is used in everyday life in terms of diagnostic and therapy. So for me, this is a really interesting field of medicine, medical engineering. So if you're also interested in this application from what you heard from this seminar or webinar, yeah, you can further learn more about this. And so once you learn all your fundamentals about this application and the technologies, then you could actually find open source databases online. So for example, this, I think the slides can be shared with your professor, and you can actually check out the links to download your open source CT data, for example, from the link I provided here. These are just one link which I provided, but there are several open source databases. You can download CT data, sinograms, and you can download MR data, which are case-based data or sometimes directly images. And you can download these data, and you can actually try to load this data, load this data in MATLAB or in Python, which is based on your interest. And you can visualize this data to see how it looks, and you can apply certain transformations and operations to see how you can manipulate the data and what effects it causes on your output image. And I would like to end this presentation by saying that you always keep on learning, because we think when we learn something, we think, okay, that is enough. But no, there are so many things that we don't know. And if we want to get an in-depth application on what is happening, then it is always better to learn more and apply this knowledge in practice, and always maintain this network which you created with all the people in order to explore more opportunities and widen your knowledge. Yes, so thank you very much. And if you have any questions, you can ask now. I think Mr. Madan or someone from your faculty would have collected questions which you have shared, because I cannot see the chat box when I'm making presentations. So hello. Yes, sir. I can hear you.
Good afternoon. Good afternoon.
Good
Myself,
afternoon,
Dr.
sir.
M. Murthy, Head Medical Electronics at Savita Engineering College. On behalf of Savita Engineering College, Management Principal, Vice Principal, Dean, HOD, staff, and students, I would like to thank you, sir. It was wonderful and highly inspirational talk on medical imaging techniques and processing. This program is an association with Savita IEEE Student Branch, Robotics and Automation, Computer, Industry Application, Women's in Engineering, Photonics, Engineering in Medicine Society. Now it is a questionnaire session. Participants raise a few questions, sir. Yes, first question.
Yes, sir.
How imaging technology play a role in radiation therapy for tumor detection?
For tumor detection, yeah. So for example, how I said SPECT and PET works. So for example, when we use radiation isotopes which emit radiation, so when we have these isotopes in our body using biomarkers, so basically you can inject them orally or you can inject them intravenously. So these isotopes or radiation sources can go to the area where there is tumor using the biomarkers. And these, when the radiation source go to the tumor site, since tumors consume more of energy and more other chemicals in order to grow more, it consumes also more radiopharmaceuticals. So when there is more radiation coming from tumor and there is less radiation coming from normal tissue, And if we are able to detect this radiation using detectors, which are present in PET and SPECT scanners, so with this radiation detection and converted to signal, and this converted signals can be visualized in a color map. And we can see, for example, if a particular area of an organ is red in color, then it is very high activity compared to normal, and we can classify it as tumor or cancerous growth. So that is how we use medical imaging for radiation in tumor detection. So I hope that answered the question, sir.
What kind of software we should know to work in nanotechnology for image processing?
Nanotechnology. Okay.
Hello?
I do not
Yes, sir.
specialize in nanotechnology, but there is one particular um, project which happens in the university where they use gold nanoparticles. So gold has high attenuation. So we use gold nanoparticles in order to track these biomarkers, like how I said. So for example, when we use biomarkers, we can use the gold nanoparticles with the biomarker and radiation source. And we can use normal X-ray imaging because X-rays are attenuated higher by the atoms which have high attenuation numbers. So for example, metals. So that was X-ray imaging or X-ray fluoroscopy is one technique which we can use to measure nanoparticles, provided they are metals. But it depends on the nanoparticles. So I do not have much knowledge about what kind of nanoparticles are there. But if they are metal or some kind of high density nanoparticles, then we can use X-ray imaging. And if the nanoparticles are also hydrogen based, which are basically protons, then we can use MR imaging in order to measure or in order to see the movements of the nanoparticles inside the body. So X-ray imaging and MR imaging are possibilities of measuring nanoparticles.
Sir. So can we use machine learning image processing technique for just X-ray classification purpose?
Yes, and also due to the recent coronavirus crisis globally, pandemic, there are a lot of institutes and research institutes and other institutions who are also using machine learning applications in order to classify chest X-rays. So, like for example, as I showed in the slide, that was just one example from an online course which I did. So there are online courses where you can learn how X-rays can be classified using machine learning models. So a model basically is trained on, say, 1,000 examples of X-rays, chest X-rays, and these examples will have normal and abnormal chest X-rays. So your machine learning model basically learns the features of these normal and abnormal X-ray images, and it will be stored as separate weights. And once we feed new images, which we take from real time or any other data, these new images can be classified by the model based on the training weights and training parameters. So machine learning can be used to classify chest X-rays, but the important factor to consider it is whether it is how accurate it classifies your data and how wide your data is. So for example, if we train our model only on one particular type of image, if you feed that model a different type of image, it won't be able to classify that image correctly. So it depends on various factors, but in general, yes, we can use machine learning and other deep learning models to classify chest images. And it is being done currently in terms of research.
Thank you, sir. Sir, what is the advanced level of Python?
I am also actually fairly new to Python because I started basically in January of this year. Yeah. So I am also exploring various opportunities which we can use, different libraries which we can use in Python in order to do image processing or in general visualize data. So I would suggest start with the basics from reading data, manipulating data. There are different packages which are used to apply linear transformation or apply different operations on data. So I am also in that level. So I do not have very advanced knowledge in terms of programming in Python, but I would say start with this and we could see where this goes ahead.
Yes, sir. Thank you, sir.
Thank you.
Dear participants, wait, sir. Dear participants, feedback form is posted in chat box. If anyone not getting certificate today, we will send it within 2 days to your mail ID. Our next webinar series are laser and its application on 20th June by Engineer Jagadish, Executive VP, Laser Science Service Private Limited, Chennai. Second, rehabilitation engineering in medical field on 21st June by Engineer Karthik Nadeshan, Research Scholar, Texas, USA. Thank you. Thank you, Aditya, sir.
So if there are any further questions, and if you do not want to ask these questions, or if you do not get any questions now, then you can always contact me either through LinkedIn or through email, and I would get back to you as soon as I can. And always, I will be always in touch. So if you have any further questions, you can always contact me.
Sir, Aditya, sir.
Yes, sir.
Any online courses available for medical imaging? Medical imaging, any online courses?
There is no one particular course which is used only for medical imaging. So there are different image processing related courses in MATLAB and also in Udemy for Python and in Coursera for Python. So Udemy and Coursera have, and also MATLAB has different image processing related courses. But once we do these image processing courses, then we get the principle and ideas behind how we can manipulate images, and we can try that on medical data. It is just applying that knowledge on medical data, but there is no one particular course for image processing. But there is a course on Coursera, coursera.org or coursera.com for AI in medicine, which is basically artificial intelligence in medicine, where we use neural networks or deep learning techniques for chest X-ray classification, MR data segmentation, and so on. So that is one of the course which I did. So I think maybe the students will find that useful. So it is AI in medicine in coursera.org, I guess. Yeah. So that is one course that I would recommend.
Thank you, sir. Thank you, sir.
Thank you, Aditya.
Thank you, Aditya, sir.
Yeah, I would also like to thank you, Dr. Murthy and Mr. Madanlal and Savita Engineering College for giving me this opportunity to share my knowledge and my little experience on various medical imaging application and techniques that is used in medical electronics or biomedical engineering. And I hope students found it useful, and they can always contact me. Whatever I know, I can share some information with them regarding in general medical engineering or biomedical engineering and medical imaging. Yeah.
Feedback link. Hello, Madan.
Sir. Feedback link put sir.
Hello, Madan.
Hello.
Madan.
Sir.
Next webinar series registration link. Next webinar series registration link.
Okay, sir.
Okay.
Yes, and if there are any questions from students, then you can simply contact me. If you are not asking in the chat now, then I can answer them later by email or LinkedIn.